Welcome to Chemistry 111. Just a quick reminder that you can always catch this after the fact up on YouTube. I've been pretty good about loading them up the same day. Try to get them up before noon, but sometimes upload speeds being what they are can take a little while. Usually, so far, I've uploaded them all to YouTube, The Chemistry Cowboy, the same day. Let's go ahead and jump right into Chapter 3. So, Chapter 3 is all about compounds, how do we name them, and introduction of the mole. So we're going to do all the basics of looking at atoms and compounds and all that before we get into how do we understand the atoms and compounds individually. So this one split into two parts. In fact, there's two homework assignments, two assessments. One part is almost all naming. The other part is almost all math. But the math is maybe a little shorter, you see, and hopefully we'll have dimensional analysis down such that it's not as bad as it first seems. But okay, start off with naming. So the major focus is chemical nomenclature, which is our systematic approach to naming compounds. So one thing you'll be asked on the test and in the homework is turning chemical formulas into names and names into chemical formulas. That, remember, a chemical formula is made up of atoms in a formula unit. The quantities of each element is represented by a subscript. So we're going to break things down into two different classes of compounds based on what is combined together. We're going to go back to our periodic table and look at that and say, what is a nonmetal and what is a metal? And depending on how these guys are mixed together is depend on how we're going to name it. So if we have two or more nonmetals together, they're going to be called a molecular compound. This is because when we have two or more nonmetals, they typically form what's called a covalent bond, where electrons are shared within that and becomes a molecule. So it's not a give and take. It's a kind of a beneficent sharing of electrons to make this a stable compound. Now, when you take a metal, which is typically positive, with a nonmetal, which is typically negative, we form a repeating 3D lattice. That we're going to have the what's called electrostatic interactions, which is the positive negative interactions, kind of like a magnet. And so we cannot define this as just one single unit, but actually it's a crystal structure. And because of that, they're going to have a completely different naming structure. And so those are called ionic compounds. So metal and non-metal make an ionic because they have ionic bonds. And two nonmetals together are going to be a molecular compound because they have covalent bonds. So the first thing before we go any further is looking at diatomic elements. There are certain nonmetals that will form molecules in the pure elemental form in order to stabilize the electron count. It helps to remember them, but it's hydrogen, and then moving across the table after carbon, we have nitrogen, oxygen, fluorine, and then moving down from fluorine, we have chlorine, bromine, and iodine. That in order to make them stable, sorry, give me a second. In order to make them stable, they will double up. Hydrogen will, as we'll learn in a couple chapters, will want to have 2 electrons. Each hydrogen typically has 1 electron. So by doubling up, they share the 2 electrons to make everyone happy. Fluorine has 7 electrons and wants 8. So it will share an electron with another fluorine to give both of them 8. The same thing with chlorine and bromine and iodine. All these guys are going to be stabilized by these molecular bonds. So these guys, when we talk about elemental oxygen, we're talking about O2, not O, because these guys are how they're typically stable. This is how we're going to find them in nature. So anytime we mention nitrogen, we're going to assume it's N2 and not N. Okay. Now, we're going to jump right into naming molecular compounds. Molecular compounds, we're mainly going to deal with binary compounds, meaning two nonmetals. So we're going to split it into two separate parts. We're going to use prefixes to tell me the subscript, because due to the nature of molecular compounds, there is many different combinations that can still be stable. We could have NO, NO2, NO3, N2O. All of these would be a nitrogen oxide compound, but without any way of stating them, without any way of separating them, how do you know which one I'm talking about? And so prefixes will say, oh, I have two nitrogens, one oxygen. I have one nitrogen, two oxygens. One nitrogen, three oxygens. So we're going to name one of these guys and then the other of these guys, and we're going to add some prefixes. Now, there's an exception. If the first element is 1, we leave the prefix off, but all other elements will get the prefix. So the prefixes, real quick: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Probably not going to use all of those, but they're right there on this side. Mono, monotone, one tone. Di or bi, like a bicycle. Tri, tricycle. Penta, the pentagon has 5 sides. Hexagon, octagon are stop signs. Decagon, decade, 10. So we're going to use those to say what subscript we have. So when one of these guys will be named like a cation, which we'll talk about in a minute when we go to ionic. The other guy's like an anion, which means he'll get an anionic ending, which is we change the ending to IDE. So you may have heard of this when I talk about carbon dioxide. Carbon dioxide. The carbon is named like a cation where it has no special ending. The oxygen goes from oxygen to oxide, gives the IDE ending. Now, based on what we just talked about with the endings, with the prefixes, sorry, dioxide, di means 2, so we're saying CO2. Now, when we name these guys, typically we're going to name these guys from left to right in the periodic table and from bottom to top within a column, with the guy further down or further left taking precedence, usually. There's an exception to this as well, but so carbon is to the left of oxygen, so carbon gets named first. In the case of nitrogen and oxygen, nitrogen is to the left of oxygen. Nitrogen gets named first. So NO would be nitrogen monoxide. NO2 would be nitrogen dioxide. NO3 would be nitrogen trioxide. So now there's an exception that halogens, which is the group to the right of oxygen, will precede oxygen for certain reasons. But so if I had ClO2, we would call that chlorine dioxide, not dioxo monochloride, dioxygen monochloride. So there's that major exception. But for the most part, we'll name left to right. We'll give them a prefix. And if the first guy's 1, we leave it off. So it's not monocarbon dioxide. Just carbon dioxide. So we're just assuming the first one's 1 unless told otherwise. So NF3, nitrogen is to the left of fluorine, so we call that nitrogen trifluoride. Now we have P2S3, we call that diphosphorus trisulfide. Phosphorus is to the left of sulfur, so we name phosphorus first. Now, we're going to have occasionally some H is considered a non-metal. But when we deal with H is going to make acids, and those guys are going to be named differently. So we're going to cover them later. But there are some compounds with H that aren't an acid, like NH3, which is ammonia, and PH3 or phosphine. We might have to memorize those, but those aren't going to be a big part of the homework, big part of the test. But those are weird ones. But either way, we don't typically call that and nitrogen trihydride. We don't worry about that one. That has a special name. But so all the elements except for H will follow this path if we talk about non-metal bound to non-metal. So let's just look at some practice. So non-metal and metalloids. So silicon, and because there's 4, tetrabromide. As I said, carbon dioxide. We already did that one. Now, we all know this is water, but if we call this by its name, that would be dihydrogen monoxide. Dihydrogen monoxide. Now, the reason I bring this up is because there's a fun little trick you can play on people where you can send around a petition banning dihydrogen monoxide, talking about how it's polluting our waterways and streams, that it's making up it's a contaminant in our food sources and in our fruits and vegetables. It's used in nuclear power plants, pesticides, and washes into the riverways. And you can get some people without the common sense to sign a petition saying they want to ban water. Causes so many deaths per year. So dihydrogen monoxide, it sounds dangerous, but it's really just water. So sulfur's below oxygen, so we call this sulfur trioxide. So this one, diarsenic pentoxide. So penta or pentoxide. And some of this comes from recognizing the elements. Tellurium hexachloride. Antimony mononitride. Dinitrogen triselenide. And this one, carbon monoxide. So CO2, benign. CO, pretty dangerous. Carbon monoxide. We're just naming these guys based on, oh, come on. Okay. Naming these guys based on the bimolecular rules. All these guys are nonmetals or metalloids, and you're putting these together with the prefix, and all these guys are getting an IDE ending. Okay, now jumping straight into the ionic compounds, which was going to take us the majority of the work here. So we're going to combine a cation with an anion together. Now, for this to be a true ionic compound, we're going to add plus and minus together so that the net charge is 0. if they don't cancel out, it's still an ion. It's not an ionic compound. We're going to mix the total positive and the total negative together to get net charge of 0. Now, the simplest ratio of cation to anion will be called the formula unit. This is because sodium chloride, which are table salt, we may say 1 sodium, 1 chloride, but in reality, we have, well, quadrillions of like molecules all put together into the structure of repeating NaCl, 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 up, down, left, right, front, and back as we talk about these guys later in the semester and next semester. And so we can't really define this as one compound that ends at any one point, but we can look at a repeating structure. And that repeating structure has 1 Na for 1 Cl. Now, in order to put these guys together, we have to understand what are the common charges of the cations and the anions. So, in order to do that, we need to look at our periodic table. I don't have one right here in front of me, but I know enough of this that I can tell you. Typically speaking, group 1, group 2, and group 3 only have one set charge. They only have one possible charge, so we can combine them together because we always know the charge. But when it comes to the transition metals, so like copper and lead and tin and iron, we can often have more than one positive charge, and so we'll have to deal with that separately. So like sodium chloride, I know it's Na and Cl because Na is +1 and Cl is always -1. So we're going to combine one positive with one minus. One positive, one minus cancels out to give 0. If I say potassium carbonate, and we'll get to carbonate in a bit, carbonate is always 2 minus. So we're going to always have to add 2 potassiums to cancel out the 1, 2 minus. So 2 1 pluses cancels 1 2 minus, giving us a net charge of 0. If I talk about sodium oxide, oxygen is typically -2. So we'd have 2 plus 1s, 1 minus 2. And a different thing, peroxide is always, each oxygen is -1. So 2 minus 1s cancels with 2 plus 1s. So how do we name monoatomic ions of one charge? So the positive ions with the one stable oxidation state, one stable charge state, and there's a couple transition metals. We will just name these guys by saying the name. If they're an ion by itself, we'll just say zinc ion, magnesium ion, potassium ion. In a compound, we're just going to say it's potassium or magnesium or zinc. So that's how we're going to deal with these normal cations. This is going to save us. All group 1 metals. All group 1. So if you look at, that's the first column on the periodic table. All want to be +1. And I'm going to hop to a periodic table in a little bit, and we'll look at that. All group 2 metals want to be +2. Group 3 metals, so like boron and aluminum, really. Those are the two main ones. Boron and aluminum want to be +3. And zinc wants to be +2. That's a transition metal, but it's special. And silver, it's a transition metal, but it's really special, want to be +1. So these guys are always this charge when they're in a compound, so we don't have to specify them. When we look at the anions, we're going to take the base name and replace the ending with IDE. So oxygen goes to oxide, chlorine goes to chloride, sulfur goes to sulfide. So, and that's going to be how we're going to, when we combine these together, we're going to have cation and anion. I realize these are bad examples because these are getting into the other thing. But so if I had ZnCl2, I would have zinc chloride. That's all I'd have to name it. So, okay, how do we predict the charge? So the easiest way to predict the charge is by looking at this table. Now, we'll get to this in, I think, another 2 chapters. But in the meantime, how do we look at this? So elements want to get to that noble gas configuration, that column 8, that helium, neon, argon, all that. So we're going to either gain or lose electrons to get there. When I move to the left, I'm losing electrons. When I move to the right, I'm gaining electrons. Remember, I said metals typically want to lose electrons and become positive. Nonmetals typically want to gain electrons and go negative. So with that in mind, lithium, if I'm moving left from column 1, I would be moving into the helium spot. So how many jumps do I have to make? I have to make 1 jump. So it's going to take 1 electron loss. Sodium, be jumping into this spot right there. Also 1 electron. Potassium, 1 jump. Rubidium, cesium, all these guys take 1 jump. Beryllium right here takes 2. We move 1 electron lost, gets it like lithium. 2 electrons lost, gets it like helium. Even though there's this big gap in the table, aluminum takes 3. 1, 2, 3 gets us there. So group 1, group 2, and group 3A or 13 will all typically be the charge of their group number. Now looking at the nonmetals, the most common ones, nitrogen, oxygen, fluorine, phosphorus, sulfur, chloride, selenium, bromine, iodine, they want to gain electrons because it's closer to move right than it is to move left. So fluorine, to get to neon here, we move 1 electron to the right. So we're gaining an electron, becoming 1 minus. Chlorine, 1 electron. Bromine, 1 electron. So it's essentially repeating this pattern. Oxygen, 2 electrons. Nitrogen, 3 electrons because it's 3 jumps. Now carbon's one of the tricky ones. I could go 4 to the right or 4 to the left. It's right there in the dead center, and so that one's kind of iffy. It depends on what we're mixing it with. Carbon dioxide, it's 4 plus. Methane, which is a gas, is 4 minus. So you have a big change between those two. But using that, we can predict the possible charges of many of these common guys. And so you'll be using the periodic table to help you determine what is the charge. Now you notice some of these guys in the transition metals have 2 numbers in it. So we can't just know for sure. Chromium could be 2 plus, 3 plus, or 6 plus, and that's not even shown. But manganese could be 2 plus or 3 plus. Cobalt can be 2 plus or 3 plus. Nickel, 2 plus, 3 plus, 4 plus. Copper, 1 plus, 2 plus. Gold, 1 plus, 3 plus. Mercury has 2 possibilities. So lead and tin have 2 possibilities, and we'll talk about those guys a little bit later. But because of that, we can't just say, oh, I know what the charge of that will be. And so we have to do our best, and we'll talk about how we do that in a bit. So when we name these guys, when we name transition metals typically have more than one charge state. If we're going to name them, we're going to name them with ionic charge in Roman numerals. We're going to say, what is the charge? And label that. So if I say iron, it's iron 2 or iron 3. If I just say iron, we don't know which one it is. So iron 2 is iron II. Iron 3 is III. If I had 4, remember that's IV. 5 would be V. 6 would be VI. 7 would be VII, and we're not going past 7, and I doubt we'll even get to 7. But note, this is the Roman numeral is the charge. Not every element will have every Roman numeral. We do not have an iron 1. It skips straight to iron 2 and iron 3 because iron 1 is not stable. We only exist as iron 2 or iron 3. So, when determining the charge of candidate, we look, and if this is in a compound, and we don't see this right away, we don't see a charge to look at, we have to look at the anion to give us help. So copper, we'll take copper 1, copper 2. We have tin 2, we have tin 4. This one's a little hard because they're both mercury 2. But what's special about this guy is there's 2 mercuries. Mercury in the +1 state is a diatomic. So that's mercury 1 and mercury 2. Mercury's a really weird ion. But I guess we already know that because remember, mercury's the only metal that is a liquid at room temperature. Okay, I'm going to actually, I just want to see where we're going. Okay. So, I'm going to take a side break real quick rather than following on with the slides. So, unfortunately, I don't have board work. But since I don't seem to have it in my notes, I'm going to just have to verbally discuss this. So as we combine these together, practice these. We need to be able to combine cations and anions together. Cations and anions together in such a way that they cancel out. So if I were to say, I'm going to jump back to our periodic table. If I was to say beryllium chloride, what would be the mixture of that? So I would look at this beryllium 2 plus, chlorine 1 minus would give us BeCl2. I would have to combine 1 plus 2 with 2 minus 1s to get that there. Fortunately, I'm not sure I have a good sheet of paper or something to work this out on with me. So we'll just work it as I see fit. Let's see if I can do it. Let's see. So, yeah. Okay, let's see. Let's see if this will show up. Okay, yeah, glare. BeCl2. I got that because I had B2 plus and Cl1 minus. Okay. And I saw that in order to make that work, I kind of have to close the blinds. Yeah. Nope, still glare. In order to make that work, I needed to combine 2 plus with 1 minus. Okay. Okay. Let's look at another one. If I had a little harder one, if I have Mg magnesium oxide, I look, Mg is 2 plus, O is 2 minus. How am I going to do that? I'm going to, one cancels the other, so the structure is going to Mg1, O1. So just MgO. I can leave the O's, the ones off, as that's understood. Now, one more tricky one before I look at some of these transition metals. If I wanted, say, mix aluminum sulfide, AlS. So how am I going to mix this together? So this one's incredibly hard because, okay, aluminum is 3 plus, sulfur is 2 minus. So what combination am I going to be able to combine that? I'm going to start, well, if I double the sulfur, I would have 4 minus. 4 minus doesn't cancel out aluminum. So if I triple the sulfur, I would have 6 minus. Then I could double the aluminum to get 6 plus. So out of the structure, that would be like Al2S3. Al2S3, where it would have 6 plus cancel 6 minus to have a neutral structure. So as we combine these together, we will be making neutral structures. Now, if I do the transition metals, in order to figure out the charge of this element, you look at the structure itself, or we look at the name. Say, for example, if I said iron 3 chloride, iron 3 by definition is iron 3 plus. Cl chloride is always 1 minus. So which way would I combine this together? 3 plus to cancel out 1 minus. I need to triple up the chlorides. FeCl3. FeCl3. So we will be combining these together. Now, if I gave you just the structure FeCl3 and you're trying to figure out what is the charge on iron, we have to work backwards. Chloride is 1 minus. There's 3 chlorides, so we have a total of 3 minus. So to get all those to cancel, we need 3 plus. So iron would have to be 3 plus. Now I'll probably hit this again in a little bit, but I wanted to make sure we hit this before we went on to polyatomics. Otherwise, I'm going to run too far ahead and get into the weeds before we get through the basics, and then we'll be too far lost. So we're going to combine these guys together in ways that will cancel each other out. Positive cancels negative to make a neutral compound. Okay. So now all these guys we've been combining together would be one metal, one non-metal to make a compound. But sometimes the positive charge or the negative charge is made up of a combination, its own little molecular ion. and these are called polyatomic ions. Poly, like polyamorous, means many. So polyatomic means many atom ions. Now, most of them are ionic, anionic, but there's a few cationic. Some of these we'll have to memorize, but there are some rules here. We're going to have some flashcards. Now, most of these guys will fit onto the oxyanions, which means we're going to have a metal or a nonmetal mixed with some amount of oxygen to get an anion. Examples of oxyanions would be sulfate, SO4, nitrate, NO3, nitrite, NO2, perchlorate, ClO4, and permanganate, MnO4. And most of these guys will have at least two structures containing different amounts of oxygens, but with the same charge. So you know, NO3 1 minus, NO2 1 minus, but the ending will change by ATE or ITE. I just want to, okay, there's the rest of them. Okay. So now I've highlighted the ones that we'll see more commonly in orange. The ones that are less common are in green, but they're still good for the pattern. So there's some patterns between this. So we can memorize this. You can flashcard this. You could just memorize the elements themselves, and you'll probably won't see them most of the time. But here's ways to hopefully mind us. Oh, shoot. Sorry. Thank you. I'll jump back. Thank you. Okay. So we're talking about sulfate, SO4 2 minus, nitrate, NO3 minus, NO2. Okay. So, yeah. So there's some rules. We can use flashcards. You might just want to memorize the most common ones, but if your mind works in a way that you see patterns, use this for your advantage. So remember that how many jumps it takes to make it to the right, make it to the noble gases. Now, like each oxygen is -2. And as we put this here, so carbon, in this case, carbonate is acting as +4. And if we put 3 oxygens to make it an anion, 4 minus 6 is -2. Carbonate. Carbon is in group 4, so it's being +4. Boron, which is in group 3, is +3. When I add 3 oxygens, it makes it 3 minus 6 is -3. Nitrogen is group 5. If this is +5 and I subtract 6, I get -1. Now, following that same pattern, 3, 2, 1, oxygen cannot do that because it would be 0. Oxygen does not have an oxyanion. If I did the same pattern with fluorine, fluorine would be a +1. 7, group 7 minus 6 would be +1. There is no oxyanions for fluorine. So the first thing we note is that row 1, when we look at any of these oxyanions, does not go above 3. It does not go above 3 oxygens. This has to do with how small these atoms are. So they cannot hold more than 3 oxygens. Now, as we do this, the charge is related to where they are on the table. 3 minus is through group 3, 2 minus, 1 minus. Now, nitrate when we lose an oxygen, we have nitrite. And we don't go any lower than that. On the next row, they're bigger. And all these guys from then on are bigger. And so they can hold 4 oxygens. Now, if 3 oxygens meant -6, 4 oxygens meant -8. So carbon was 4 minus 6. It gave us -2. So silicon, 4 minus 8 would be -4. You see it dropped down by a charge of 2. Phosphorus, group 5, 5 minus 8 is -3. So phosphate. Sulfur, that was oxygen didn't have one, it would have been 0. But 6 minus 8 makes it -2. And now fluorine, 7 minus 8, -1. So the charge is 4, 3, 2, 1. 3, 2, 1. 2, 1. Down all these guys except for the first row are -2. All these guys except for the first row are -1. -1, -3, -3. -2, -4. So just looking at this pattern right here. Now, sulfate, SO4, sulfite. We won't see selenate, but if we did selenate, selenite. We won't really see tellurium, but tellerate, tellerite. We see a pattern here. Now, the halogens, except for fluorine, have 4 possible structures. So instead of having chlorate and chlorite, we have to specify the difference between all 4. So we use per and hypo to differentiate these 4 structures. Now, this comes from biology. If we hear hyper, which is we shorten to per in this case, hyper means above. Like if I'm hyperthermic, I'm running a fever. My temperature is running above normal. Hypothermia is my temperature running below normal. So when I say perchlorate, I'm saying I'm running 1 oxygen above chlorate. So perchlorate, chlorate, chlorite, and then hypochlorite, I'm running 1 oxygen below chlorite. These guys are the ones you may see. Perchlorate is probably the most common one you'll see. As I said, there are some rules. You may want to just flashcard and memorize a couple of these common ones, especially the nitrogens, the phosphorus, the sulfur, the chlorines, and the carbon. But if your mind works and sees some of these patterns, you can see, oh, 1 minus, why does this jump to 3 minus? Well, this jumps to 3 minus because we add another oxygen. Why does this one at 2 minus? This is 2 minus because it's group 6. 6 minus 8 oxygen, 8 from oxygen makes this -2. Please note, phosphite does not exist normally, but hydrogen phosphite does. So you would think phosphate would get phosphite, but it's just not stable. And so we need a hydrogen in there to make it stable. But okay, so other polyatomics. Some of these are common, some of these are not so common. So hydrogen carbonate, we'll probably see that a lot. So if carbonate was CO3 2 minus, when I add a hydrogen, hydrogen is in group 1, hydrogen will typically want to be +1. +1 to 2 minus makes this 1 minus. So hydrogen carbonate, also known as bicarbonate. So if you use sodium bicarbonate, you're using NaHCO3. But that's hydrogen carbonate. Hydrogen sulfate, probably won't deal with that too much, but SO4 2 minus, we add a +1, it becomes SO4 1 minus. Hydrogen phosphate, dihydrogen phosphate, hydrogen sulfide, hydrogen phosphate. Permanganate, you may hear of this. We'll use this in lab sometime next semester. Chromate and dichromate, probably not going to really come up too much. You guys are probably not going to come up too much, but these are examples of metal oxyanions. These are ones we'll see more often. Hydroxide. Learn that one. Memorize that one. That will come up. OH 1 minus. Hydroxide. O is 2 minus. H is +1. You combine -2 and +1. What do you get? -1. Hydroxide. Cyanide. That fun little poison. CN1 minus. Acetate, we'll use this guy. Either you can learn it C2H3O2 1 minus or CH3CO2 1 minus. But acetate is the ion that's going to be present in vinegar. Acetic acid, as we'll learn. When we remove a hydrogen, we get acetate. Oxalate, we'll occasionally see peroxide, and here's the one positive charge one we'll see. Ammonium. If NH3 was ammonia, NH4 is ammonium, and we'll see that. So typically, as we add a hydrogen to an oxyanion, the charge goes up by 1, and we'll add a hydrogen in front of the name. Acetate, cyanide, and hydroxide are relatively common. Ammonium is the only really cation we'll see. So you could mix ammonium chloride. Ammonium chloride would be NH4Cl. We will finish with this slide, but we will practice a lot more in the coming days. I'll look at some of the homework in the coming days, but this is where we'll get to for today. So we have to turn these guys from name to structure, structure to name, and oh, there's a goof there. That should be neutral. But so KOH. So K is potassium. Potassium is group 2. So it is, oh, sorry, potassium is group 1. So we don't need a symbol. It's just K, potassium hydroxide. Sodium sulfate. So sodium is group 1. We don't need any special charges. Well, we have to recognize that's sulfate. Zinc. This is a hard one. Zinc chlorate. Because perchlorate is ClO4. So 1 oxygen less would be chlorate. And lastly, magnesium magnesium hydrogen phosphite. Because I'm breaking this down into magnesium, then hydrogen phosphite. So magnesium and then hydrogen phosphite. It's because phosphate is PO4. So we're going to go from PO4 to PO3. So I change it from phosphate to phosphite. Now coming to the actual turning these into compounds. So cesium, group 1. Cesium is +1. Cyanide, -1. So I'm going to combine these together as cesium cyanide, CsCN. Magnesium acetate. So magnesium is 2+, acetate is C2H3O2 minus. So in order to combine these together as a neutral compound, I'm going to have to double up the acetate. Now here's the trick. Because C2H3O2 is, the whole thing is doubled, I'm going to put this in parentheses before I put a 2 behind it to double up the whole structure. I need to double up the whole structure. Rubidium, which is +1, nitride, which is -3. So I'm going to triple the rubidium. And then ammonium chloride, I already did this one, but NH4 plus and Cl1 minus. So I can keep it as NH4Cl. Now, some of this stuff will only come with practice, and we'll continue with more practice. And it's just, we got to bow. We got to work together here and understand that it's a lot. And we went through a lot of naming. And so we're going to just hit practice tomorrow on Wednesday before we move on. That's as far as we're going to go today. Thank you for your time. I understand this is a difficult time for everyone. Have a good day.